All right, hello everyone. This is Dr. Caudell, and we're back for more on Chapter 6, so thermochemistry. The next topic we're going to get into is now calculating the specific heat capacity. And so all the topics we're going to go through in this part of Chapter 6 are pretty interrelated, so we're going to use similar equations and get through some similar topics. So within this first topic, we start to introduce the concept of calorimetry. So here's a constant pressure calorimetry where no heat enters or leaves what's happening within the system here. So some reaction is taking place. We can have these styrofoam cups that somewhat insulate the reaction so that ideally no heat is entering or leaving from the reaction. Then we have a stir to keep the solution mixed, what's happening in the reaction. So we don't have things that are concentrating on one side of the vessel and concentrating on another side. So we're stirring it to keep it thoroughly mixed and then measuring the temperature. So this is what's referred to as a coffee cup calorimeter. We also have a bomb calorimeter, but they're very similar in principle. So in this coffee cup calorimeter, we are saying that no heat enters or leaves the calorimeter system. That's not always true, but in an ideal coffee cup calorimeter, again, no heat is leaving or entering. So when the reaction occurs, heat released from the reaction heats up the water, only the water within the calorimeter. Then by measuring the change in temperature of the water, the heat released by the reaction can be calculated. So it's a pretty convenient way to put a reaction in this vessel, then measure the temperature change of the water that surrounds the reaction, to then get information about what heat is released or absorbed by the reaction itself that's taking place in this coffee cup calorimeter. So our bonds breaking, our bonds forming, we can tell what's happening because whatever is happening to the reaction, we will see that as a result of what's happening to the water. Is the water gaining heat? Then that means the reaction is giving off heat. Is the water losing heat? That means the reaction is absorbing heat. So as mentioned, if the water is getting colder, that means the reaction itself is absorbing some of the heat from the water. What kind of reaction absorbs heat? And remember, heat is represented by Q. So that was first mentioned in part 1. So this is an endothermic reaction. So an endothermic reaction or an endothermic process, this absorbs heat, right, throughout the reaction. And we could tell that by the water getting colder. Then if the water is getting hotter, that means that the reaction itself is releasing some heat into the water. So what kind of reaction releases heat? So this kind of reaction or this kind of process is an exothermic process. Let's try this practice problem now. So a chemist carefully measures the amount of heat needed to raise the temperature of a 486 milligram sample of a pure substance from this temperature to this temperature. The experiment shows that this many joules, remember J is joules, it's a unit of energy. What can the chemist report for the specific heat capacity of the substance? So we're going to use an equation to help us solve this, a very useful equation within this chapter. So before going through and solving this, let's set the stage for using this equation. So we're asked about the heat capacity. The specific heat capacity of a substance is the amount of heat needed to raise the temperature of 1 gram of a substance by 1 Kelvin. We can think of a specific heat capacity as something like the price of a Kelvin of temperature rising. How much energy do we need to increase the temperature of a substance by 1 Kelvin? So it takes more heat to, quote, buy a Kelvin when a substance demands a, quote, high price. In this scenario, the high price equates to the idea of a substance having a high heat capacity. So for a high heat capacity, the substance needs more energy to raise the temperature by 1 Kelvin. So not all substances have the same heat capacity. It depends on the atoms and the bonds that make up a pure substance. So if you've heard the phrase that water, H2O, has a, quote, high heat capacity, That means that it takes a lot of energy to raise the temperature of water by 1 Kelvin. So let's say over the winter, we had some lake of water that froze. As the temperature starts to heat up, it's going to take a lot of heat to fully melt that frozen lake because water has a, quote, high heat capacity. So then something with a low heat capacity, it doesn't take as much heat to raise the temperature of 1 gram of that other substance with a lower heat capacity. So going back to this sort of price analogy, to calculate the price of something, you divide the total cost of what you bought by the amount that you bought. For example, if you bought half a pound of coffee for $6, you could divide the total cost, $6, by the amount, or 0.5 pounds, to find the price per pound, right? So you could say that we took $6, that bought us just 0.5 pounds. Then taking this divided by this tells us how much we needed per 1 pound. Or for the specific heat capacity case, how much heat we need per 1 gram of the substance. So similarly, to calculate the price of each Kelvin of temperature rise for the substance, the chemist should divide the cost of the temperature rise, or in this case, the heat used per gram of the substance. This is divided by the amount of the temperature rise it bought, or the number of Kelvin the temperature rose. So this is helping us set up how we get this equation for specific heat capacity. So we're building up to this equation, and in this equation, this capital Q is the same thing as our heat. This C is our specific heat capacity. This M here is the mass, and this delta T here is the change in temperature. Remember, for any of these deltas, the delta T is always final minus initial. So T final minus T initial. So the specific heat capacity of each substance can be determined by how much heat was needed based on how much mass of the substance was present and how much of the change in temperature there was. Was there an increase by 15 Kelvin, 5 Kelvin, etc.? So we're going to use this equation a lot in chapter 6. And the way that I like to word this equation instead, as an easy way to remember it, is I like to say that Q equals M cat. So Q equals MC delta T, or Q equals M cat. That's supposed to be a little drawing of a cat there. So this is an easier way to remember it, I think. So Q equals M cat. We're going to use this version a lot as well. And so heat can be represented as lowercase q and uppercase q. So same thing here. So again, Q stands for the total heat used. M is the mass of a pure sample. That's important because specific heat capacities are for pure samples. And then delta T is the temperature change. So going back up to our problem, let's start to associate some of these numbers with the variables in that equation. And we saw that specific heat equals Q over M delta T. Again, I really like to start out with Q equals M cat and then see what I can plug in, and knowing that I will need to solve for the specific heat because that's what we're asked for. So the mass here, this is 486.0 milligrams. So not in grams, we'll probably have to do a unit conversion. Then this delta T, we know, needs to take into account T final minus T initial. So when we read this, a pure substance from this temperature to this temperature. So this means 16.4 degrees C is our final temperature, and then negative 6.1 degrees C for our initial temperature. Then we were told that it took 2.57 joules of heat. So Q can be in joules, it could be in kilojoules, here it's just in joules. So that is our Q term. Then we can plug in these different values and solve for this specific heat. Remember, this is the same thing, just using uppercase Q versus lowercase q, then rearranging this to solve for the specific heat capacity. And we're remembering that the specific heat capacity is per 1 gram of the sample, so we will need to convert milligrams into grams. Let's start with the delta T. So we know we're taking T final minus T initial. T final is 16.4 degrees C. T initial is negative 6.1 degrees C. Do we need to convert this into Kelvin before we do the subtraction? Well, fortunately, the answer is no, because this would be 16.4 plus 273, or 273.15. Then negative 6.1, also plus 273. So if we did convert these into Kelvin first, we would add 273 and add 273, then end up with a delta T that's in Kelvin. Now, technically, this is the same delta T if we just left this in Celsius, because we're adding 273 to this term and we're adding 273 to this term. So really, this delta T comes out to be the same. This means for us, we don't have to convert into Kelvin. So we don't have to convert into Kelvin first for a delta T, so for that change in temperature, because we add 273 to both terms anyway. So 16.4 minus a negative 6.1 is the same delta T as 16.4 first plus 273, then minus a negative 6.1, also plus 273. So we just need to take T final minus T initial, where we make sure we include that negative sign here. So 16.4, then the two negatives make a positive, plus 6.1. So our delta T is 22.5, technically degrees C, but now we also know this is the same as a delta T in Kelvin, which is what we want for a specific heat capacity. So for that specific heat capacity, we want 1 gram and we want it in Kelvin. So far we do have that delta T term that we've dealt with. We know we need to convert milligrams into grams, then Q is already in joules. So let's say I'm starting with Q equals M cat again, but I know I'm going to divide both sides by M delta T. So that means specific heat capacity comes out to the heat over M delta T. So we have delta T. We need to convert milligrams into grams. So 486.0 milligrams, there are 1,000 milligrams in a gram. So we're moving this decimal point over 1, 2, 3. So that is 0.486 grams. That's going to go into our mass term. We need mass to be in grams. We have a delta T that's in Kelvin, and we have a Q in joules. You could convert milligrams into grams at the end as well, but I like to do it before I plug it into my mass term. So Q is heat, that's 2.57 joules. As a refresher from part 1, heat is a form of energy. Then energy we typically see in joules. And then mass in grams, then delta T, technically in Kelvin. We do this multiplication and then the division overall. We get a specific heat capacity, 0.235, technically in units of joules per gram Kelvin. These are typical units for a specific heat capacity, so in joules per gram Kelvin. So watch out for different unit conversions that we need. Fortunately for the delta T, we didn't have to convert each individual temperature into Kelvin, because delta T in terms of Celsius is the same delta T in terms of Kelvin. So in solving this one, we say the chemist can report 0.235 joules per gram Kelvin as the specific heat capacity of that pure substance. As a reminder here for those negative exponents, 0.235 joule, gram negative 1, Kelvin negative 1. Remember, this negative 1 just means that it's in the reciprocal, right? So 0.235 joules, this is really per gram Kelvin. You can also denote these as a negative 1 exponent, so then these are all in line. Let's also do 6.7 together. That's in the main slide deck. So more on using, this is a coffee cup calorimeter. So another example of this, we have a lead represented by Pb, so that chemical symbol from the periodic table, A lead pellet has a specific mass of 26.47 grams. It starts at 89.98 degrees C. It's in a constant pressure calorimeter or a coffee cup calorimeter. The coffee cup calorimeter itself has a negligible heat capacity, meaning that it's not going to absorb any heat or change temperature itself, ideally. Right, so no heat is leaving or being entered into the system. So we're saying the heat capacity of the calorimeter itself is negligible. We'll talk about an example where it's not. That gets into bomb calorimetry. So here though, let's get back to this one. So negligible heat capacity containing 100 milliliters of water. Then we know the water temperature rose from 25.50 degrees C to 23.17 degrees C. Then what is the specific heat of the lead pellet? So this is a little bit more complex of an example, so I wanted to do this one together. So we can really think of Q equals MCAT. We can think of a Q equals MCAT for water, and at the same time, a Q equals MCAT for the lead. Let's see what we know so far, or what we could figure out based on what's given in the problem. So the lead has a specific mass. We are given that, so 26.47 grams. We know that it starts at a specific temperature, but we don't know where it ends up, or at least we're not told explicitly what the temperature is. We want to solve for this specific heat capacity, and we know that whatever is going to happen to the lead, the heat given off or absorbed, we'll be able to tell that by the temperature of the water. So for the water itself, we could look up the specific heat capacity of water. Then we could also have a delta T of water. What about the mass of water? Well, we don't have a mass of the water, but we do know it's 100 milliliters of water, and we could use the density of water to get the mass. Now, if you're asking, well, couldn't we just also then look up the specific heat capacity of pure lead? Well, technically, yes, but you might also see a problem like this that says we have some unknown metal, and it's at this mass with this starting temperature. So you're not always told what metal it is, and here we're asked to figure out the experimentally determined specific heat capacity of lead. Okay, so we're going to practice calculating that. Of course, theoretically, we could look it up, then compare our experimental value to the theoretical value. Generally, for these sorts of problems, we do assume the theoretical heat capacity of water, so the surrounding solution of that reaction. So we'll look at the heat capacity of water, and then an important connection we're going to make is that the heat given off or absorbed by water is going to be the opposite of the heat given off or absorbed by the metal lead. So whatever is happening to lead, we can tell that by what's happening to the water and vice versa. We're assuming that the walls of the calorimeter itself don't absorb any heat because we're told this specifically in the problem, that the constant pressure calorimeter of negligible heat capacity. So we're not going to worry about the styrofoam walls absorbing any heat. We're just going to think about the system being the reaction that's taking place, and then the surroundings are the water. And that's all we're considering, so these two components. So it is a good idea to sketch this out if it's helpful to you. So here we have a sketch of the initial and final situations. We have 100 milliliters of water. The density of water is 1 gram per milliliter. So for 100 milliliters, we'll actually calculate this two together. That's 100 grams of water. It starts out at this temperature, then the lead gets placed into the water. So it's not technically a reaction that's taking place. We're just putting a piece of metal that's at a different temperature into water. Then we're going to have a heat exchange until the temperatures equilibrate. So a hot piece of metal into water, it's going to heat up the water and also cool down the metal. We know the volume of water, we can figure out the mass of water. We also know the mass of the lead pellet. We also know the initial temperature of the lead and the initial and final temperature of the water. Another big important connection we need to make is that in the final scenario, the temperatures are equal. That means the temperature of the lead is going to equal the temperature of the water. There's going to be a heat exchange between the lead and the water until they reach the same temperature. Based on the heat capacity and how much water there is, and based on the heat capacity and how much lead there is, that tells us how the heat exchanges between the hot piece of metal and the colder water. Going back to part 1, this is an example of an isolated system, meaning no heat is lost to the surroundings. In an isolated system, then, all we're considering is the heat of the lead itself and the heat of the surrounding water. Nothing else is at play, so these two together have to equate to 0. If this heat of the lead goes up, the heat of the water has to go down. If the heat of the water goes up, then the heat of the lead has to go down. Energy, including heat is a form of energy, cannot be created nor destroyed. So whatever is lost by one object has to be gained by another, and vice versa. So the way to think about this is that the heat of the lead is the opposite of the heat of the water. This is also a completely okay way to write it out. Heat of the lead equals positive heat of the water. We know the signs are going to be opposite. We don't know yet, we haven't thought about, is lead going to lose heat and then water is going to gain heat, or is water going to lose heat and lead is going to gain heat? So that's where these signs come in, and we'll have to think about those. Right now, we're just saying that whatever is happening to lead, the opposite is happening to water. Then again, Q equals M cat, so Q of the lead is equal to M cat, where this is the mass of the lead, specific heat capacity of the lead, and the delta T of the lead. Then Q equals M cat for water. That's also the mass of the water now, specific heat capacity of the water, and delta T of the water. What you may see is that specific heat capacity can also be represented as S. So specific heat capacity you'll see as S or as C. So specific heat capacity. So both of these can go in here. Then very importantly, delta T, any of these deltas is always final minus initial. So T final minus T initial, that would go into this term here and this term here, given the initial temperature of the lead and the initial temperature of the water. Then, as mentioned on the last slide, the final temperatures of both are going to be equal. At the end of the exchange of heat, at the end of the heat exchange, the final temperature of the water is going to be equal to the final temperature of the lead. Heat is going to exchange until this temperature is the same as the surrounding temperature. That's when all of the heat has equilibrated and heat is no longer being actively transferred from the metal to the water or the water to the metal. There is still going to be some minor exchange of heat, but ultimately we're going to see that as an equilibrium. So no more net heat is exchanged either way. They end up at the same final temperature. We'll see how this helps us solve this problem. Let's first solve for the heat of water, then we'll think about the heat of lead, knowing that whatever's happening to water, the opposite is happening to lead. So Q equals M cat, the mass of water, 100 grams. How do we get that? Well, we know we started out at 100 milliliters of water. The density of water is 1.0 gram per milliliter. This is the symbol rho, also denoted as D. So density, or rho, is equal to 1.0 gram per milliliter. Remember, density is love, or mass, over volume. So in order to get grams of water, we take the density, we put grams in the numerator, 1.0 gram per milliliter. Then milliliters and milliliters cancel out. Then we do have 100 grams of water. That's how much 100 milliliters weighs. So that goes in right here. Then the specific heat capacity of water. This is one to memorize or just have noted. So specific heat capacity of water is going to show up a lot. So 4.184 joules per gram degrees Celsius. So some specific heat capacities are in joule per gram degrees C or joule per gram Kelvin. Fortunately, again, the delta T term, we don't have to convert these both into Kelvin. They can just remain in Celsius. That will get us the same delta T for both Celsius and in Kelvin. So T final minus T initial is the delta T of the water. The water temperature rose from 25.50 to 23.17 degrees Celsius. So T initial 25.50, T final 23.17. So T final, T initial, we do the subtraction here, then we multiply through. Let's see what the units work out to. So just looking at units, this mass is in terms of grams. Specific heat capacity of water, we are using joule per gram degrees C. Temperature final, we could use these and denote them as either degrees Celsius or Kelvin. So this doesn't end up mattering. So this is a delta T in terms of degrees Celsius. Then degrees C cancel out, grams and grams cancel out. We get heat in terms of joules. So this is what we want, right? Heat is a form of energy. So we expect that unit to be in joules. Now Q equals MCAT for the lead. So MC delta T. Let's think about what we know. We know the mass of the lead is 26.47 grams. We're solving for the specific heat. The delta T is T final minus T initial. We know the metal started at 89.98 degrees C, and because the water and the metal will end up at the same temperature final, then T final here we weren't told explicitly, but for the metal, that's also going to end up at the same final temperature as the water. So there will be a heat exchange till they end up at the same final temperature. So we plug in 23.17 degrees C for this term as well. Now we know whatever's happening to water, the opposite is happening to lead. But let's really think about this sign here. So the water is starting out at 22.5 degrees C, then it heats up to 23.17 degrees C. Then for lead, it starts at very hot, so 89.98 degrees C. Then as the temperatures equilibrate, it also ends up at that 23.17 degrees C. To figure out the sign of Q, if Q is positive, that means heat is being absorbed by whatever has a positive value for Q. If Q is negative, that means that heat is being released. Is the water absorbing heat or releasing heat to go from 22.5 degrees C to 23.17 degrees C? Well, the temperature is increasing. For the temperature to increase, it means that water is gaining heat. For the lead to go from 89.98 degrees C to 23.17 degrees C, it means the lead is losing heat. So the water is gaining 280.3 joules of heat, right? It's positive. That means the lead itself is losing that amount of heat to the water. That's why Q of lead, the heat of lead, is the negative version of this number. It's the negative value. So 280.3 joules, negative 280.3 joules. Water is gaining heat, lead is losing heat. Whatever heat water is gaining is being lost by the lead. Therefore, we then equate the negative heat of lead is equal to the positive heat gained by water. So then Q of PB, or the heat of lead, is now negative 280.3 joules. The only unknown here is solving for the specific heat capacity of lead. We could rearrange this now to solve for S, which is the same thing as solving for C in that Q equals MCAT equation. So to rearrange this and solve for C/S, that's the same thing that we saw in the first practice problem. So specific heat capacity C is equal to Q over the mass times delta T. So we plug in what we know for delta T. Here's our heat, here's our mass. Then we solve for the specific heat capacity of lead, report that in joules per gram degree C. This could also be joules per gram Kelvin too, right? Because this degree C minus this degree C, that delta T could also be in terms of Kelvin. Just depends on what the question is asking for. So we could report this final answer here as 0.158 joules per gram Kelvin or joules per gram degrees C. We actually more so see specific heats listed as per degree C. But we'll see what other practice problems we come across and go from there. So let's go on to the next topic now. If you have any questions about calorimetry, please let me know. This is a pretty big topic in Chapter 6. And again, in this lecture, this part of Chapter 6, we're going to do a lot of practice with that Q equals MCAT equation and different variations of calorimetry. So now using specific heat capacity to then find the temperature change. So still using this equation to find now delta T instead of solving for the specific heat capacity. So let's go through this explanation now. So the specific heat, or S, of a substance is the amount of heat Q required to raise the temperature of 1 gram of the substance by 1 degree C. Similarly, the heat capacity, or represented as C now, of a substance is the amount of heat, or Q, required to raise the temperature of a given quantity, or mass, of the substance by 1 degree C. So in the specific heat capacity, it's more specific, right? It's how much heat is required to raise exactly 1 gram of some substance. Whereas the heat capacity C is how much heat is required to raise the temperature of a given quantity, not necessarily 1 gram. So in terms of units, the specific heat capacity, or S, is how much heat, so joule, required to raise the temperature of 1 gram, so G, of the substance by 1 degree C. Then heat capacity, or just C, is the amount of heat, so also joules, required to raise the temperature of a given quantity or mass of the substance by 1 degree Celsius. So these will end up being very similar, and I'll try to distinguish them as best I can as we go through these sorts of practice problems. So here we can say that because the heat capacity, or just C, is joules per degree C, let me write this in the same color to make it clear, then times a mass term, which we know is in grams, multiplied by the specific heat capacity, that is joules per gram degree C. So the units work out because grams and grams cancel out. Then joules per degree C is equal to joules per degree C. So specific heat capacity is on a per gram basis, whereas the heat capacity is not as specific. It's just for any amount of that substance. A tip to solving all these sorts of problems is just focusing on the units here. As long as our units work out, then we'll get an answer that we want. So Q equals MCAT, then technically Q is also equal to just capital C, or the heat capacity, times delta T. So specific heat capacity, lowercase s, or lowercase c, whereas the heat capacity, just uppercase C. So what I mean by looking at just the units and focusing on those to help us solve these problems, if we're given a heat capacity, or uppercase C, and that's just in units of joules per degree Celsius, then multiplied by the change in temperature, also in degrees Celsius, the units work out to give us Q which is heat, a form of energy, we know that needs to be in just the unit of joules. So if we have a heat capacity without a mass term, then we don't need to know a mass to plug in here to solve for the heat or the energy. This one, though, if we're given a lowercase s or lowercase c specific heat, that's going to have units of mass incorporated into it, right? So the lowercase s or lowercase c, that is joules per gram degrees Celsius. The delta T is also, let's say it's in degrees C. We also need a mass term because we have to cancel out this gram unit to just get joules in the end, which is what we want for heat or energy. So as long as we're paying attention to the units, we'll know if we need to incorporate a mass in grams or if we don't need to incorporate a mass in grams because we just have a heat capacity, not a specific heat capacity. Then again, delta T is always the final minus initial, so T final minus T initial. Here are some specific heats, so lowercase s or lowercase c. We recognize that because grams are incorporated into these values. So for example, these pure substances can have very different specific heats. Here's water as mentioned, so that 4.184 joules per gram degrees Celsius or joules per gram Kelvin. So water is relatively higher even compared to some of these metals. Then mercury has a lower specific heat compared to iron, for example. So it just depends on the makeup of these different metals or different compounds. Water, again, has a relatively high heat capacity amongst a lot of materials. Let's try this practice problem and we'll go through and be really clear about Q equals mc delta T, where that's a lowercase c, versus Q equals capital C delta T. So a chemical reaction takes place inside a flask that's submerged in a water bath. The water bath contains 2.80 kilograms of water and it's at 29.3 degrees Celsius. During the reaction, 113 kilojoules of heat flows out of the flask and into the water bath. So this heat exchange, this is 113 kilojoules of heat exchange from the flask to the water bath. As far as signs, let's practice this before going further. So if this reaction is exchanging heat to the water, does this reaction have a negative or positive Q, a negative or positive heat? Well, it's losing this much heat, right? So that's going to be a negative value, and the water itself is gaining that heat. Okay, so it's really important to keep thinking about the signs here, especially in chapter 6. Calculate the new temperature, so we know it's T final, of the water bath. We can assume the specific heat capacity of the water under these conditions is that 4.184 joule per gram Kelvin. We know this is the same thing as 4.184 joules per gram degrees C, right? So that delta T can be the same for Kelvin and Celsius. It's not the same for Fahrenheit, but we won't really work with Fahrenheit here in chapter 6. So let's start solving this now. I want to point out that, again, the flask is losing heat, right? So heat is being exchanged to the surrounding water bath. Let's think about if that is an exothermic or endothermic process. So a chemical reaction that releases heat or energy into what's around it, in this case, the water bath is around it, this is an exothermic reaction. So the system itself is this flask. Heat is lost by the system. It's important to define what is our system. Heat is lost by the system to the surrounding water bath. When heat is lost by the system, that is an exothermic reaction, as opposed to this reaction flask absorbing heat. If that were the case, that would be endothermic. Here it is losing heat. It is an exothermic reaction or an exothermic process, depending on what's happening in this flask. So since heat flowed into the water bath, the temperature of the bath must have increased, right? When heat is exchanged here, the temperature is going to increase of the water. The temperature is going to decrease for whatever's in this flask. How do we calculate exactly how much the temperature of the bath changed? So whenever we need a connection between heat flow and temperature change, think specific heat capacity, or that equation that we've used a few times, or we're going to continue to use, that Q equals M cat, where this term here is our specific heat capacity. I grew up using Q equals M cat to remember it rather than Q equals M sat. So C here is still the specific heat capacity. It's different than the capital C there for just heat capacity. So I'll try to keep that really clear as we move forward. Remember, specific heat capacities include that joule per gram Kelvin or joule per gram degrees C. Specific heat capacities are more specific. They take into account it's on a per gram basis. That's one way to think about it. So this is an exothermic reaction. It releases heat into its surroundings. We've seen this equation a few times. Based on what we want to solve for, we can rearrange this equation, where Q is the amount of heat that flows into or out of the system, right? We always think about in reference to the system. That's a review from part 1. M is the mass of the substance. Delta T stands for the change in temperature, where that's always T final minus T initial, or the final state minus the initial state. So in solving these types of problems, we're going to think either heat capacity or specific heat capacity. Because we're given a mass amount of water and we know the specific heat capacity of water, we're going to think this equation. Let's see what we know that we can plug in based on the information we're given. Well, here we have 2.80 kilograms. That's how much water surrounds it. Why does mass matter? Well, if we have more water around this reaction vessel or hotter vessel, more water means that the temperature of the water will not heat up as much, right? If there's more water to heat up, that final temperature won't be as high. If there's less water, then all that water surrounding the hotter vessel is going to heat up faster relative to if there was more water. Here we have 2.80 kilograms of water that surround this hot vessel. We are also told that during the reaction, this much heat flows out of the flask and into the water bath. So for heat relative to the flask, that is losing 113 kilojoules of heat. Heat for the water bath, though, it is gaining that much heat, right? So we can equate these heat terms as long as we show that they have the opposite sign. We don't equate these terms for the specific heat capacity or the change in temperature or the mass, but we do equate these heat terms for the system and its surroundings, right? So here is our system, here is the surroundings. Whatever heat is lost by the system, the heat is gained by these surroundings. So we can equate these heat terms or Q values. So we have a mass, we do have a Q value. We are given the specific heat capacity for water. That is 4.184 joules per gram Kelvin or joules per gram degrees C. Now for this delta T term, we know that is composed of T final minus T initial. Calculate the new temperature of the water bath. So we are going to calculate T final, but we are told that it starts out at 29.3 degrees Celsius. So T initial of water, 29.3 degrees Celsius. Let's plug in Q, M, C, and T initial, then make sure we can rearrange and solve for T final. So the specific heat capacity of water is that 4.184 joules per gram Kelvin or joules per gram degrees C. Let's convert Q into joules. because it was given to us in kilojoules, but let's go ahead and convert that. So that was 113 kilojoules. There are 1,000 joules for every 1 kilojoule. Then kilojoules and kilojoules cancel out. We're taking this value times 1,000. So that many joules. Now we have a value for Q we can plug in where the units will work out. The specific heat capacity, again, joules per gram Kelvin or joules per gram degrees C. So we need our mass term to be in grams. It was given to us as 2.80 kilograms, and for every 1,000 grams in 1 kilogram, kilograms and kilograms cancel out. Then we have this, moving this decimal point over 3 times, so 2,800 grams. When we multiply by 1,000 or divide by 1,000, we can move the decimal point over 3 times to the right if we're multiplying by 1,000, or 3 times to the left if we were dividing by 1,000. So that's going to be plugged in here for the mass. Then for the delta T, again, we're solving for T final and we have T initial. So let's go ahead and rearrange for delta T. So delta T is going to be equal to this many joules of heat. The mass is 2,800 grams. The specific heat capacity for water, 4.184 joules per gram Kelvin. Again, these are interchangeable, joules per gram degrees C or joules per gram Kelvin, because the delta T term here, delta T is the same in Kelvin and in degrees Celsius. So at this point, we would cancel out grams and joules, then be left with 1 over Kelvin. We know this goes into the numerator then, because that's really 1 over Kelvin. So then Kelvin is the unit we have for temperature. For a delta T, that is the same. If we need to, we can state that instead as degrees Celsius for the same value we get here. That calculates to a delta T of 9.6548 with some other numbers. First in Kelvin, that is the same because it's a delta T. That's the same as this number, also in degrees Celsius. So that is one benefit of the delta T term. It's the same for Kelvin and for Celsius. So we're going to solve for T final. Delta T is always T final minus T initial. We just found the delta T on the last slide to be 9.6548 with some additional numbers. We can keep those sig figs for now. Degrees C, we want to change that into because our initial temperature was given in degrees C. This is also the same as 9.6548 Kelvin because it's that delta T, but again, we can state this as degrees Celsius instead because our initial temperature was given as 29.3 degrees Celsius. So let's go ahead and plug that into our delta T term. So then we're taking this value for the delta T and adding 29.3 degrees Celsius. We should get a T final of about 38.955. Because we're working in degrees C, then we can plug that in, so say degrees C for our units. For a subtraction style problem, addition or subtraction, for a review on sig figs, we can have the same number of digits past the decimal point. Here there is an infinite number if we didn't round. In the value we're given in the problem, though, we look at, right? So there's 1 digit past the decimal place. That means we need to make this T final have 1 digit past the decimal place. This is going to bump this 9 up, making this 39.0 degrees C. So the new temperature of the water bath comes out to 39.0 degrees Celsius. There is a similar problem in the main slide deck and in your textbook, so example 6.5. Again, if you have any questions at all about these types of Q equals MCAT problems or calorimetry problems, please let me know, and we can go through some more practice problems together in office hours, for example. Okay, so again, these topics build on one another and use a lot of this idea of Q equals MCAT. So I wanted to put all these topics together to keep them straight and organized. So let's keep going in the same realm and now solving a basic calorimetry problem. So the constant pressure calorimeter, that was what we called a coffee cup calorimeter. Now a constant volume calorimeter is what we call a bomb calorimeter. So in that coffee cup calorimeter, that styrofoam, we essentially didn't worry about the styrofoam absorbing any of the heat. For this kind of bomb calorimeter, we do take into account sometimes the heat that is absorbed by the material itself. So this metal material that makes up the bomb calorimeter. So now we're taking into account the reaction itself, the water that the reaction is surrounded by, and now the material of the bomb calorimeter, usually some type of metal. So we're going to consider the reaction taking place, the water that is absorbing some of the heat, and the material of the bomb calorimeter itself. So with no heat exchange beyond what's involved in the water, the bomb calorimeter, and the reaction, we can equate all of this to be zero. Whatever is happening to the water has to happen to the bomb calorimeter material, has to happen to the reaction. If this one goes up, these two might have to go down, or just one of them goes down. So now we've introduced a third sort of variable here for these bomb calorimetry problems. So for instance, if we're interested in just the heat of the reaction, we'll need to consider the heat of the surrounding water and the heat of the surrounding bomb calorimeter material. For the water, we know we can represent that as Q equals M cat, where this C is the specific heat capacity. We care about the mass of the surrounding water. Now, however, for the Q equation for the bomb calorimeter, we no longer care about how much material there is. What I mean by that is the Q of the bomb calorimeter is now capital C for just the plain heat capacity, not the specific heat capacity. That means for a bomb calorimeter, you're not going to see a value like we saw for water. So like 4.184 joules per gram degrees C. Instead, for this heat capacity of a bomb calorimeter, you're going to see just units of just something arbitrary here, like 99 joules per degree C. We no longer care about the mass of the calorimeter. We do care about the mass of the surrounding water. We do care about the mass of the components of the reaction. For the bomb calorimeter itself, though, we're just going to see a heat capacity with units of joules per degree C, no longer joule per gram degree C. And we will practice using different heats for the bomb calorimeter, the reaction, and for the water. Then the enthalpy altogether, we'll come back to this. It's not exactly equal to the heat of the reaction. It's approximately equal to the heat of the reaction. So we'll come back and I'll point out what you need to know more about this delta H term, or that change in enthalpy we initially saw briefly in part 1. So a little bit more of an explanation on these bomb calorimeters or constant volume calorimeters. And again, the constant pressure calorimeter, we commonly refer to as a coffee cup calorimeter. But here in a constant volume calorimeter or a bomb calorimeter, a sample is placed into a small cup with a closed container known as a bomb. These calorimeters can be a little bit dangerous in the lab setting. Not as dangerous as a real bomb, but they can be dangerous, especially with different reactions taking place and different pressure buildup. So 2 wires lead to the sample and oxygen gas enters through the inlet at the top of the bomb. This bomb portion then is then immersed in a calorimeter bucket that's filled with water, and the entire setup exists within an isolated jacket. The entire calorimeter is a closed system. If you remember what a closed system is from part 1, for a closed system, no heat enters or leaves the calorimeter. It's not an isolated system, it's not an open system, it's a closed system. So I first covered these different types of systems in part 1. When the ignition circuit is closed, the sample combusts within the bomb. Heat is released from the combustion. It heats up the water within the calorimeter. So by measuring the change in temperature of the water, the heat released by the sample combustion can be calculated. For these bomb calorimeters, though, we also need to consider what's happening to the material of the bomb calorimeter itself as well to get information about what's happening within the reaction. Here we're told we have 54.7 grams of iron, has a specific heat capacity, meaning we're going to see mass in here. The calorimeter contains 200 grams of water. The temperature of the water starts off at 15.0 degrees C. When I read things like this, I might write a note to myself and say temperature initial starts out at 15 degrees C. When the temperature of the water stops changing, it's at 17.2 degrees Celsius. The pressure remains constant. When we read that it's a constant pressure actually tells us that we're working with a coffee cup calorimeter problem. Within a coffee cup calorimeter problem, we may or may not worry about the heat of the calorimeter itself. If we're not told any information about the heat of the calorimeter itself, then we usually negate it. Let's keep going here and see what information we have, see what we need to calculate. So calculate the initial temperature of the iron sample. We're not told anything about the calorimeter, so now the only components we really are worried about are the Q of the iron and the Q of the water. So again, Q equals mc delta T, Q equals mc delta T. I like to start to assign what information we have about our different components. Again, we're not told anything about the calorimeter itself, so in this case, we're just focused on the iron and the water. We have the mass of the iron as 54.7 grams. We have the specific heat capacity of the iron to be 0.449 joules per gram degrees C. Then we do have the mass of the water, so 200 grams. The temperature of the water, so Ti, starts out at 15.0 degrees C. When the temperature of the water stops changing, it's at 17.2 degrees C. We're at constant pressure. This told us we're in a coffee cup calorimeter. Then we're going to calculate the initial temperature of the iron sample. Before going to this, I want you to think about, do we know information about T final of the iron? It's not given to us in the problem, but what connection can we make about the iron and the water? Over time, they will exchange heat to where the final temperatures are in equilibrium. That means the final temperature of iron will be the same final temperature as the surrounding water. So this is also at 17.2 degrees Celsius. Again, it's not told us explicitly in the problem. It's not told to us explicitly, but that is a big connection we need to make. The iron and the water will end up at the same final temperature. So one idea we've seen in part 1, the most important idea in this problem here is a conservation of energy. We've essentially been dealing with this throughout this part in chapter 6, where no energy can be created nor destroyed. Whatever happens to the water, the opposite is going to happen to the other material, in this case, the iron. If iron loses heat, water has to gain that heat or that energy. If water loses energy, iron has to gain that energy. We have to conserve energy. It can't just be created out of nowhere. Here, this tells us the thermal energy that the iron loses as it cools down is the same energy absorbed by the water as it warms up until they reach that same final temperature. So the other key idea here is that the amount of thermal energy, delta E, also think of that as Q, The amount of thermal energy, or the amount of heat, right? Heat is a form of energy a substance absorbs or loses is linked to its change in temperature through its specific heat capacity, C or S now, right? And mass M. So again, not to be confusing, but little c or little s, these are both the specific heat capacities. Then capital C is just the heat capacity. And we see a delta E here, or a change in energy, if we're thinking about in reference to a final minus initial kind of scenario, right? So energy final minus energy initial. We might be looking at final and initial conditions as far as a substance absorbing or losing some amount of thermal energy. Where does it start at? Where does it end up at? That's where that delta E comes into play. So we can use the heat capacity equation to calculate the change in energy from a delta T, or by rearranging it to calculate a delta T from a delta E, or a C from a delta T, and so on. I'm going to show you how we can still keep thinking about it as far as Q equals M cat. In essence, this Q does represent the change in energy because it's based on how the temperature is changing. So let's keep going. Let's work towards solving this. So overview of solving this, we know the change in temperature of the water. We also know its mass, and we can find its specific heat capacity using a table in our textbook or using an ALEKS data resource. That means we can calculate Q, or the thermal energy. So Q is heat, and heat is a form of energy. Because of the conservation of energy, that's equal to then the heat, or the thermal energy that the iron is losing. So we've kind of been building up to this topic in the same way we've been doing the past practice problems here in part 2. We know the mass and the heat capacity of the iron. We can rearrange this equation to then calculate its change in temperature. We know, here's the important point here I've been talking about, since its final temperature must be the same as the final temperature of water, then we can use the change in temperature to find the sample's initial temperature. Just to say it again, T final of the water is going to equal T final of the sample. Here our sample is iron. They're going to exchange thermal energy in the form of heat until they reach the same final temperature. Let's first look at the heat of water. So Q of water equals MC delta T. We do know the specific heat capacity of water is that 4.184 joules per gram degrees C, or 4.184 joules per gram Kelvin. We also know the water starts out at 15 degrees Celsius, then goes to 17.2 degrees Celsius. We also have the mass of 200 grams. So delta T is T final minus T initial. We know that we can plug in 17.2 degrees C for T final and 15.0 degrees C for T initial. That delta T comes out to 2.200. We'll keep sig figs for now. That is degrees C. That is the same thing as 2.2000 Kelvin, right? If we added 273 here, or we added 273 here, then that delta T term comes out the same despite us keeping it in Celsius, both in Celsius, or converting both into Kelvin. So this delta T of the water is 2.200 degrees C, or Kelvin. The mass is 200 grams. So now we have everything to solve for the heat of the water. 200 grams, grams and grams cancel out. Change in temperature, 2.200 Kelvin or Celsius. If we stick with Celsius, then Celsius and Celsius cancel out. Then we're left with just heat in terms of joules, which is the unit we want. So the heat of water comes out to 200 times 4.184 times 2.200. That comes out to 1814 joules, and this is again for the heat of water. So this slide here shows what we just did. Instead of writing out as delta E, it's okay to just think about it as the heat. So the heat of water is based on how the temperature of the water is changing. So the heat is the same thing as the change in energy. And again, we get 1,841 joules for the heat or the change in energy, change in thermal energy of water. We need to think about the signs importantly. So is the water gaining heat or is the water losing heat? The water starts out at 15 degrees Celsius, then goes to 17.2 degrees Celsius. The temperature is increasing. That means it is gaining heat or gaining thermal energy. That means this water amount will be a positive sign, and then the amount of heat or thermal energy for the iron must be the negative sign. So Q of the water, 1,841 joules, that is gaining heat. That means due to the conservation of energy, that means that iron, heat of iron, I'll put the negative sign right here, it must be losing that much energy, that much thermal energy. It's not our final answer. This does help us then solve for the temperature of iron. We know based on what's happening to water, how much energy water is gaining, how much heat water is gaining. That is the same as how much energy or heat the iron is losing. So that negative sign means it is losing heat. Now we can take this and then still think about Q of Fe being equal to mc delta T. This has to be the mass of iron, specific heat capacity of iron, change in temperature of iron. So Q of iron equals mcat. Q of iron must be negative 1,841 joules. Do we know the mass, specific heat capacity, or delta T? Let's go back up to the setup of our problem and see what we assigned so far. So mass of iron, 54.7 grams, specific heat of iron, 0.449 joules per gram degrees Celsius. So 54.7 grams, the specific heat capacity, 0.449 joules per gram degrees Celsius. Grams cancel out so far. We need to figure out what's in our delta T term. That is T final minus T initial. To keep it simple right now, we can just say delta T so far, then we'll come back and figure out, do we know the final temperature, which we do, right? It's the final temperature of water. The final temperature of iron and the final temperature of water are the same. Let's keep this as delta T though to make the rearrangement algebraically a little bit more simple. So delta T is Q over MC, and the Q value is negative 1,841 joules. MC, we had 54.7 grams. C is 0.449 joules per gram degrees C. Grams cancel out, joules and joules cancel out. This is 1 over 1 degrees C, so that's really just degrees C. That unit makes sense for what we want because we want a change in temperature. Doing the division here and multiplying these, we should get a change in temperature equal to negative 74.96 degrees Celsius. Importantly, the delta T, we have to be really careful about the sign, is always T final minus T initial. Based on our problem, we want to solve for T initial. And again, we know T final because we know the final temperature of the water bath. The final temperature of the water bath is 17.2 degrees Celsius. That means the final temperature of iron also then equilibrated to 17.2 degrees Celsius. So plugging in that value there for the T final, we can then solve for T initial by taking negative 74.96 minus 17.2 degrees C. Then there's still this negative sign out front. So then we would be multiplying both sides by -1. Then the negative sign cancels out on the other side. T initial then 92.16 degrees C. We need to consider sig figs here. We were told to just have 2 sig figs in the end. So this answer, 92.16 degrees C, just needs 2 sig figs. So our final answer then is 92 degrees Celsius. That was T initial of the iron sample. So what we did was take the notion that Q equals M cat. We equated Q for water and Q for iron to say something like Q of water equals negative Q of iron. Then we plugged in what we knew from iron and for water, so MC delta T and MC delta T. We knew the mass of water, specific heat capacity of water, delta T of water, and we knew the mass of iron, the specific heat capacity of iron, and the T final of iron. Then we solve for T initial using the fact that delta T equals T final minus T initial. So we need to stay really organized here and be able to solve for these different variables in the Q equals M cat equations. So now another very related topic here in chapter 6, finding the equilibrium temperature when substances are at different temperatures and they end up mixing. So still pretty similar equations to what we've seen before. Let's practice solving a problem like this. We have 11.0 grams of cream at 17.0 degrees Celsius. They're added to an insulated cup containing this many grams of coffee at a hotter temperature. Calculate the equilibrium temperature of the coffee. From what we've looked at so far, you should start to think that the T final of the coffee must equal the T final of the cream. That's when they are at thermal equilibrium. We can assume that no heat is lost to the cup or to the surroundings, so we are just thinking about the coffee and the cream. We're just going to think about the heat exchange between the coffee and the cream and assume that no heat is lost to the cup or to the surroundings. So this definitely doesn't actually satisfy a real-world scenario. We're just going to think ideally here and assume that only heat is exchanged between the coffee and the cream. So again, the key to solving this problem is combining our conservation of energy with heat capacity equation, which relates a change in thermal energy, or delta E, also thought of as the heat exchange, to a change in temperature, or delta T. This is going to look very similar to what we've set up so far, where we can say Q of the coffee equals MC delta T. That's going to have an opposite sign as the Q of the cream, or Q of the cream then is also MC delta T. They're both going to reach the same final temperature. Let's first figure out which one is gaining heat and which one is losing heat. If one is gaining heat, it's going to have a positive Q. If one is losing heat, it's going to have a negative Q. The cream starts out at 17.0 degrees C. The coffee itself is at 72.6 degrees C. So as they're reaching a final temperature, definitely the coffee is losing heat and the cream is going to gain heat. If the cream is going to heat up, the coffee is going to cool down. So negative sign for the coffee, it is going to lose heat, and the cream is going to gain heat. So from this number 1, the important part here, the final temperature of the cream and coffee must be the same. Even though the coffee starts out hotter, the cream starts out cooler, they're going to reach a thermal equilibrium to where their T finals are the same. Then, based on conservation of energy that we've seen a few times, we know that the energy lost by the coffee is equal to the energy gained by the cream. And again, I prefer to use negative Q of the coffee is equal to positive Q of the cream. Whatever is happening to coffee, the opposite is happening to cream and vice versa. If the coffee is losing heat, it has to go into the cream. We're not going to gain or lose energy. It's all going to be conserved between just the coffee and the cream because we're told we don't need to worry about the environment around these, the coffee and the cream. We're just focused on the coffee and the cream, not the air around it, not the cup. Next, we can approach this problem a few different ways. Let me show you how we're setting this up right here. So we keep in mind that the coffee is losing heat and the cream is gaining heat. We know that Q can be broken down into mc delta T and mc delta T, where m is the mass of the coffee, c the specific heat capacity of the coffee, delta T in relation to the coffee. On this side of the equation for the cream, it's the mass of the cream, the specific heat capacity of the cream, and the change in temperature of the cream. So here, plugging in the meaning, mass of the coffee, the specific heat capacity of the coffee, the change in temperature of the coffee, we still have that negative sign out front because the coffee is losing heat or losing thermal energy and the cream is gaining it. Then mass of the cream, specific heat capacity of the cream, and the change in temperature of the cream. If we can plug in different numbers that we know, then we can solve for a T final. Now it gets a little messier algebraically because delta T is really T final minus T initial. Delta T over here is also T final minus T initial. To successfully solve this problem, T final is going to equal T final. T final of the coffee will equal T final of the cream. They're going to reach a thermal equilibrium and end up at the same temperature. So now, instead of thinking of this as T final of the coffee and T initial of the coffee, T final of the cream, and T initial of the cream, T final on both sides of the equation for the coffee and the cream are going to be the same. So this is just the same value here. We can denote as just T or TF. Now we keep T initial of the coffee here because that is different compared to the cream than T initial of the cream. They will reach the same final temperature, but they started out at different initial temperatures. So we need to keep that clear in this equation. Then algebraically, we want to solve for T final. So we can do a lot of rearranging, a lot of isolating to then solve for a T final that involves the mass of the coffee, specific heat capacity of the coffee, temperature initial of the coffee, then plus mass of the cream, specific heat capacity of the cream, then the initial temperature of the cream, all divided by the mass of the coffee, specific heat capacity of the coffee, plus mass of cream, and specific heat capacity of the cream. So it definitely gets a little complex algebraically. Ultimately, we're solving for T final of both systems. They reach the same T final. So this is an option for an equation to write down. We have one object reaching an equilibrium temperature with a different object. This equation holds if you just substitute in if we have iron and water instead of coffee and cream, for example. Mass, specific heat, and initial temperature for whatever two components we want to find out their final temperature for. Now, if you're feeling ambitious, you could also theoretically plug in the various values into this equation and then eventually solve for T final. it gets pretty complex algebraically. So let's go ahead and plug in our values into this equation. So the mass of the coffee is 150.0 grams. Now, if you're wondering what the specific heat of coffee and cream are going to be, well, let's go back and see the setup of the problem. So we could assume that no heat is lost to the cup or the surroundings, and importantly, that any physical properties of cream and coffee you need are the same as those of water. So 4.184 joules per gram degrees C, or 4.184 joules per gram Kelvin. Because our temperatures here are in degrees C, we might as well work in degrees C. So we can call the specific heat capacity of coffee the same as that of water, and the specific heat capacity of cream, we can also use this value for water. The initial temperature of coffee is 72.6 degrees Celsius. At this point, grams and grams cancel out, and degrees C cancel out. Now let's do the same thing for the cream. We know we started at 11.0 grams. We're using the specific heat capacity that's the same as that of water, so joules per gram degrees C. The initial temperature of the cream is 17.0 degrees Celsius. At this point, grams, degrees C, and degrees C cancel out. So let's keep going. This is all divided by the mass of the coffee, or 150 grams, times again that specific heat capacity value, then plus the mass of the cream times the specific heat capacity again, so joules per gram degrees C. Grams and grams cancel out. Now we have joules and degrees C that remain in the denominator. So to keep everything straight, I went ahead and solved for the numerator first. Remember, we just had joules left as our unit. Then in the denominator, we had joules per degree Celsius. So that's really dividing by joules per degree C. That's really multiplying by the reciprocal. That works out. So our T final should be in a temperature unit. Joules and joules cancel out. Doing the division here numerically, we do get a final temperature value around 68.801, unrounded right now, degrees C. Then to get this into the proper sig figs, we just need 3 sig figs, so 68.8 degrees Celsius is the final temperature of the coffee and the cream together. So again, I recommend utilizing this equation to solve for any final temperature where two objects have reached a thermal equilibrium. When in doubt, you could also plug in all your values here, then solve for T final. Again, it gets a little complicated algebraically, but you could do that if you'd like to. I'm going to recommend using this equation though for any thermal equilibrium style problems. Again, if you have any questions about any of the problems in the main slide deck, in the textbook, in Alex, please let me know. I hope you're all doing well, and I will talk to you soon. I'm going to include this animation on heat flow. So again, let me know if you have any questions I can help with, and hopefully I will talk to you soon. I'm also including here some animations that are copyrighted, and they are provided by the publisher.
Consider the diagram where the universe is represented as the system and surroundings. The system is the specific part of the universe that is of interest to us. In this case, the system is the block of ice. The rest of the universe, outside the block of ice, is called the surroundings. In this animation, both macroscopic and microscopic views of ice are shown. Let's show a transfer of heat from the surroundings to the system. At 0 degrees Celsius and a pressure of 1 atmosphere, ice melts to form liquid water. To melt a solid, attractive forces around the particles must be overcome. As heat is absorbed by the solid, particles begin to move about more vigorously, and some particles break free from the attractions of neighboring particles. Measurements show that for every mole of ice converted to liquid water at 0 degrees Celsius and a pressure of 1 atmosphere, 6.01 kilojoules of energy is absorbed by the system, the ice, from the surroundings. When heat has to be supplied to the system by the surroundings, the process is called an endothermic process. Click on the button below to look at the reverse process, the freezing of water. At 0 degrees Celsius and a pressure of 1 atmosphere, liquid water freezes to form ice. As heat is removed from a liquid, the motion of the liquid particles slows down so that stronger attractive forces in the solid can form between the particles. Measurements show that for every mole of liquid water converted to ice at 0 degrees Celsius and a pressure of 1 atmosphere, 6.01 kilojoules of energy must be given off by the system to the surroundings. When heat is transferred from the system to the surroundings, the process is called an exothermic process.